Alright, so Kepler's first law states that all planets move in elliptical orbits with the center of mass of the system at one of the foci. Now, an ellipse is a circle. The difference is that a circle is an ellipse where the eccentricity is 0. So eccentricity tells you how elliptical the ellipse is. So if I set the eccentricity down to 0, you get a perfect circle. But as you increase the eccentricity up to 1, you get a more and more elongated shape. So I can make this more and more elongated. So I like to use Mercury to demonstrate Kepler's first law. If we set it to Earth, you can see here that the eccentricity is very, very small. And in fact, the sun and the empty focus are almost on top of each other, like for a circle. But if I set it to Mercury, we can see that there's two focuses, and you can sort of think of those focuses as like the center of the circle, only now there's two. So an ellipse is defined by the semi-major axis, which is the long radius, and a semi-minor axis, which is the shorter radius. And so we can draw an ellipse out by drawing radial lines. And let me start the animation and then slow the animation down. By drawing a radial line from one foci to the planet and the other foci to the planet. So as the planet orbits around, the length of radius 1 and the length of radius 2 changes, but it's always equal to 2 times the semi-major axis. So this makes it an ellipse rather than an oval. Now, this simulation has the sun sitting at one of the foci, and this is what Kepler thought was true, but Kepler did not know about Newton's laws of gravitation. So it turns out that the sun exerts a force on the planet, but the planets also exert a force on the sun. So the sun also has a teeny tiny little orbit of its own. And so we actually orbit around the center mass of the system, including the sun, rather than orbiting around the sun itself. Kepler's second law states that a line drawn from the sun to any planet sweeps out equal area in equal time. So I've set it up here so that it's going to sweep out triangles of equal area that represent 1/8 of the orbit of Mercury. So I'm going to hit start sweeping. And let's speed this up a little bit. So what you'll notice here is that the triangles when you're close to the sun are very short, but they're very wide. But the triangles when you're further away from the sun are longer, but very short. And the reason for this is so that their areas are the same. So the area here and the area over here are going to be exactly the same. And the reason why this occurs is you'll notice as Mercury orbits around the sun, when we get closer to the sun, notice the planet speeds up, and when the planet is further away from the sun, it's going to slow down. And it's going to turn out the reason for this is the conservation of angular momentum. And we'll talk about angular momentum in the next chapter. But angular momentum is going to depend upon the mass of the object, so the mass stays the same, since it's the mass of the planet, and the radial distance, so in this case, r is small here, but r is big here. So in order to balance that out, the velocities must change. So for a small number to equal big number, the velocities must be opposite. So the velocity here with the short radial distance is going to be a high velocity. So at closest approach, the velocity is going to be high, the radius is short. And at furthest approach, the velocity is going to be small because r is big. So according to Kepler's law, the distance from the planet is inversely proportional to its orbital speed. And we know that the angular momentum must be conserved because remember, we learned that dl dt is equal to the torque net. Remember, L stands for angular momentum. So if we want angular momentum to be conserved, this must be true. So that means the torque net needs to equal 0. And the torque net is equal to 0 because the only force acting on this planet is going to be the force due to gravity from the sun. And the lever arm, remember, is going to also be the distance between the planet and the sun. So since the force and the lever arm are parallel to each other, that tells us that the torque is equal to 0. So the force of gravity doesn't cause a torque on the planet. So therefore the torque net is 0, which tells us that our angular momentum must be conserved. Kepler's third law states that the orbital period, so the time for the planet to orbit around once, is going to be proportional to its distance from the sun cubed. So the full form of this equation is that the period squared is equal to the 4 pi squared r cubed divided by the gravitational constant divided by the mass. So remember, a period is the time to orbit once. And this is going to be in seconds. So the orbital period of the Earth would be 1 year, but then you have to convert that 1 year into seconds. This, once again, is distance from center to center. And this here is the mass exerting the force. Now, in this case, we don't acknowledge the fact that the orbits of the planets are not perfect circles. Kepler's second law is the only time we actually acknowledge that anywhere in this course. So other than applying Kepler's second law, we're going to assume that all orbits are circular, even though they're really not. The other thing I want to point out and overemphasize the fact that the m in this equation is the mass exerting the force, because this comes out of this relationship here. So we're plugging in our Newtonian gravitation equation, and force net in the radial direction equals mass times velocity squared over r. So the little m's cancel out, and you're left with only the mass exerting the force, not the one experiencing the force. And there's some more substitutions to get the full derivation, because you have to turn velocity into period. However, you can get the idea that those little m's cancel out so that you're only left with the mass exerting the force in the equation. And it's incredibly important for you guys to know that.